Welcome to the last topic of Tour K, Farming for the Future, Autonomous Tractors and Agricultural Robots. Farming is the backbone of economy and is the foundation that supports a growing population. We all know that we will need to feed close to 10 billion people by the year 2050. However, there are a lot of challenges we have to face in agriculture. For example, the decreased agricultural land, extreme weathers and diseases, and labor shortage. One of the solutions is developing smart farming systems. We also call it precision agriculture or smart agriculture. Smart farming can help improve farming efficiency through site-specific management. It can reduce environmental impact and boost the quality and quantity of agricultural production. You may wonder, why exactly is smart farming? We don't have time to explain it in details here, but to keep it simple, smart farming consists of three aspects. They are smart sensing and monitoring, smart analysis and planning, and the last one is smart control. Among those three aspects, two are closely related to autonomous tractors and agricultural robots. They are smart sensing and monitoring and smart control, as shown here. Now, autonomous tractors are also considered as agricultural robots. Of course, all of the autonomous functions for the autonomous tractors are designed to accommodate the general characteristics of a tractor. In general, an autonomous tractor works in two steps. The first step is to generate a work plan using collected data. For example, using GIS to generate prescription maps for various operations. These may include plan the path and speeds of the tractor, rate of various operations at each location. The second step is to operate in an autonomous way. Now, during operation, one common task for all autonomous tractors is navigation. So now we will talk about different navigation methods. One of the earliest technologies for tractor navigation is an operation support system. It uses GPS and directional sensors, for example, compass, to assist with navigation. It will show the work history and the current position and direction. In this case, the driver can do multiple tasks. If a target path has been defined, such a system will show the driver if the tractor is on the right path and how much if it's not. So basically, it will show the deviation of the tractor from the right target path. Now, navigation for tractors can be fully autonomous when operating in many types of agricultural lands, as long as there are not many tall trees or tall buildings close by. The GPS is still the primary technology used for navigation currently. However, there are risks of losing connections to GPS satellites in various situations. Therefore, researchers developed ways to integrate GPS with other sensors, such as inertial measurement unit, compass, and wheel encoders, to enhance its accuracy and reliability for navigation. For more challenging environments, such as orchard, computer vision methods are used to assist navigation. For example, cameras can be used to detect the location of trees and use that information as a reference to guide the tractor. Here I'm showing another type of navigation method. It's called automatic following system. The position of the wagon is based on the position of the harvester. This is also a very useful navigation method because it requires only one person to operate multiple vehicles. Although navigation is the foundation for autonomous tractors, it is useless without performing certain tasks. Some tasks can be as easy as doing tillage. Here I'm showing a rotary tillage. It simply uses the power from the tractor's PTO, power takeoff, to perform the tillage in the field. I say it is simple because the operation is performed uniformly on the entire field. A similar robot can be this weeding robot. The tractor provides autonomous navigation while the weeding machine uses fire to kill the weed. It relies on the fact that the weeds are smaller than the crop in this field, and the fire will only kill the smaller weeds. Again, the operation was also performed uniformly on the entire field, so that's why I say it is relatively simple. Now, typically, weeding is a relatively difficult task because in most cases, the robot needs to recognize the weeds first and then kill them. So now I'm going to show a more advanced weeding robot here. So this is the robot that is fully self-propelled and it uses solar panel to power itself. And this robot has vision systems to detect weeds. And after it detects the weeds, it will use its anti-effectors to kill the weeds. It uses two methods. One is mechanical, and the other one is using herbicides to kill the weeds. Okay. Next, I'm showing you some greenhouse robots. Greenhouse robots are usually have very complex and advanced mechanical and vision systems because a fully autonomous robot in greenhouse will need to perform fruit or vegetable picking tasks. A mechanical arm with picking mechanisms and vision systems are typically required for such tasks. Because operating in greenhouses, these robots must be compact and be able to turn with small turning radius. On top of those requirements, the most difficult part of developing these robots is to ensure the operation speed, which is what limits their usage currently. Next, I'm going to show a state-of-the-art greenhouse robot for picking sweet peppers. It is developed by Wageningen University in Netherlands. The robot uses a robotic arm, computer vision systems, and specially designed anti-effector to fulfill the harvesting task. So now let's take a look at the video.
To build the first sweet pepper harvesting robot, that was the goal of the Sweeper project. Increasing the efficiency and reducing labour dependence will ensure Europe's high-tech greenhouse food production yields and competitiveness. The robot is an assembly of an autonomous mobile platform with a robotic arm holding an end effector for fruit harvesting. The robotic arm with the end effector scans the crop for mature peppers. The camera operates completely independently from surrounding light conditions. It gives color images and a distance map. This information is used for pepper detection, localization, and maturity classification. Peppers are scanned by looking slightly upwards. By observing the bottom part of the pepper, maturity can easily be detected. The robot was trained to find obstacles like leaves and stems in the images. To speed up the training work, a simulated artificial pepper crop model and a deep learning network was used. After detection, the pepper location is used to perform a path planning for the robotic arm. This can be a complex trajectory, since the space in which the robot arm may move is very limited. The robotic arm employs visual servo control to reach the peduncle of the peppers on target. For this, it takes images from several sides. The arm approaches the pepper in such a direction that the stem is always to the backside of the pepper. The small cutting tool is positioned just above the pepper and cuts the peduncle while the cutting tool is moved downwards. After cutting, the pepper falls downwards into the fingers of the pepper catching device and is moved towards the pepper bin by the robotic arm. A conveyor belt will be added to the robot in order to convey harvested peppers to a standard pepper trolley. Multiple robots and trolleys will be part of a fully automated post-harvest logistics management system.
Now, fruit or vegetable picking is not limited to greenhouse robots, but outdoor fruit or vegetable picking is even more difficult because of added difficulties in navigation. Here, I'm showing you a strawberry picking robot. It uses a high accuracy GPS called RTK GPS for navigation, and then it uses high-speed cameras for fruit identification. And of course, here the end effector is also specially designed to pick the strawberries. Okay, agricultural robots are not limited to ground-based robots. Drones can also be considered as robotic systems. Most drones are only used for sensing purposes by carrying cameras. They are not often used for agricultural operations due to concerns of power consumption. There are three types of drones. The first one is fixed-wing drone. It is the fastest and can cover the largest areas with the least power consumption. And the second type is multi-rotor type drone. It consumes the most power. However, its ability to hover gives it a lot of advantages. For example, it can take close, high-quality images of a specific task. And the third type is the newest type. It's called hybrid drone that combines the fixed wings with the rotors. This type of drone will allow the drone to do vertical takeoff and landing, like a multi-rotor drone, and fly efficiently to cover large areas, like a fixed-wing drone. Now, for conclusion of this presentation, today we talked about smart agriculture, which includes three aspects: smart sensing and monitoring, smart analysis and planning, and the last one is smart control. Autonomous tractors and agricultural robots are typically used for smart sensing and control. Now, navigation is the foundation for autonomous tractors. Autonomous navigation can be based on GPS and computer vision, which are the most often used sensors. And sometimes we also integrate multiple sensors to assist with the GPS and computer vision to improve the accuracy and the reliability. Now, agricultural robots are not limited just to ground-based robots. Drones are also considered agricultural robots. And there are three types of drones used for agriculture. They are fixed-wing, multi-rotor, and hybrid types. So I hope this presentation gives you some useful insights of the current state-of-the-art agricultural robots. And thank you for your attention.